All right, we come on to our question about magnetism. It's a really nice one. Okay, we've got our bar magnet, our iron magnet, which picks up iron nails. Okay, remember iron, as soon as you see this iron, remember the word soft. Okay, it's a soft magnetic material. Now, you never know if that might come in useful or not. Now, what's going on in this picture is quite a subtle thing, actually. You notice that you've got your two nails hanging off the magnet, however, they're not hanging vertical. Okay, so the point here is that these two nails are really pushing each other away. If they're angled in that way, there must be some kind of force which is pushing the two apart. Now, if you remember in class when we used magnets, okay, we're doing something called inducing magnetism, and that induced magnetism is temporary. Okay, that induced magnetism is temporary. When I place a magnetic material inside a magnetic field, it becomes a magnet, and that little magnet gains a south and a north pole. Okay, now the reason that these are attracted to the magnet is because south and north are attracting to each other. However, on this side we've got another south and another north. Well, if we've got north and north next to each other, then we'll find that they will push each other away, they will repel. So, first mark that you get here is for stating basically that my two little nails have become magnets. They've been placed in a magnetic field and have been magnetized. It's called induced magnetism. Induced magnetism is a very good word to have here. We notice that these two lower ends are north poles, and therefore they will repel each other, i.e. they will push each other apart. Okay? We then jump away from magnetism to radioactivity. Here we really just want to know the definition of isotope. Okay? Isotopes, you should know, have the same proton number. Okay, you could also call it atomic number. And you could do what I almost did there, referring to mass numbers. You could also say that they have different numbers of neutrons. But I would stick with referring to the atomic mass numbers or proton and nucleon numbers. We then need to use nuclide notation. This is nuclide notation for those of you who are unsure. Okay, and remember we're balancing the numbers. This is beta decay. What you should be aware of beta decay, remember, was an electron, a fast-moving electron. And what happens during that process is one of my neutrons becomes a proton. Well, the effect of this is that this number, which represents the number of protons, must go up by 1 to 27. This number stays the same because we have the same number of nucleons. So you've got 27 and 60 up here. In this case, this is cobalt. You should be able to get this just by looking at your periodic table, which is provided. To balance the numbers, we need to have a number which adds up to 26 on this location here. Well, 27 plus minus 1 is 26. 60, therefore we've got a 0 up here, and this is beta. This is a nice question, okay, about resistance. Notice we've got a few things here. We don't actually know an equation for this. There is an equation for this, but we don't learn this in GCSE. We just learn the behaviors. You're told a resistance of 1.21 times 10 to the minus 3 ohms. Okay? You're also told a length and an area, and then a new length and a new area. What we know is that if you make a wire longer, it has more resistance. This is essentially the same as adding up lots of resistance wires in a row. You're going to have more resistance. So, similarly, if the wire gets smaller, its resistance will go down. So we say that the resistance is directly proportional to the length. Here, we are going from a length of 0.5 to a length of 0.25 meters. And so therefore we're halving. Well, if the length halves, given this proportionality, the resistance must have. With the area, it's different. If we have greater area, we have a lower resistance. In this case, we've got an area of 4 times 10 to the minus 5, and then 8 times 10 to the minus 5. So we're doubling the area in this case. Well, again, if we double the area, then due to that inverse proportional relationship, R is divided by 2. So we've got two things which are dividing my resistance by 2. In other words, we're dividing it by 2 times 2, which is 4. The new resistance is the old resistance divided by 4, which gives me 3 times 10 to the minus 4. A lot of thinking to go on in there, okay? No equation to use, unfortunately, so you have to show your thought process, and I hope that you can follow mine here. Last one, 6D. Okay, it's another calculation question, and again, another question which has 3 marks. Okay, we have a block of iron which is on a bench. The surface of the block is 144 centimeters squared. Just take a second to pay attention to those units. They're a bit awkward, those ones. Okay, but they're the same as in the question, so you probably won't have to change anything. We have the mass of the block of iron is 13.6 kg. Okay, so we essentially have this situation. We have some weight, and weight is equal to m times g. Here, make sure g equals 10 newton per kilogram. Okay, please, please, please don't decide it equals anything else. When you get to IB next year, you'll find that g changes a little bit. For IGCSE, it is 10, never anything else. Pressure is force divided by area. The force equals the weight, which is just equal to mg. So therefore, pressure is mg divided by area. We have a mass of 13.6. Okay, that's m up here. We've got an area up here, and so all we have to do is divide 0.94. And the reason this is a 3-mark question is simply because you've got to do 2 bits of calculating.